Hello friends, welcome to Tech Tool. In this video we will discuss how we can minimize a DFA. First of all, you may be wondering that how do we need to minimize a DFA? So let's take an example for this. Suppose we have to draw a DFA that will accept all the strings over a comma b containing at least one symbol. So if we draw the DFA with a simple approach, you may start with a state q0, that will be your start state, and you have to accept at least one symbol. So let's accept at least a or b. Then you can make a transition to a state q1, and here also you can you may make you may draw DFA like this. Okay, so one may draw a DFA and he may say that this is a DFA that will accept all the strings over a comma b containing at least one symbol. Fine, and this is absolutely fine DFA. But one may argue that you can also draw the DFA with only two states. Here you can see that these two states are redundant. You can also draw the DFA as you can start with Q0, you accept at least one symbol, then you can directly jump to the final state. Fine. There is no significant change in this and this DFA. Both are equivalent in nature. But in our this first DFA, we have two states that are redundant. We will call all these states as equivalent states. The states that can be merged together to form a single state. That states are your equivalent states. So whenever you see a DFA, that DFA may or may not be minimized. So you have to follow some procedure to minimize that DFA. Here the DFA was very simple, so you can minimize the DFA by just looking at this DFA, but in some complex DFAs you have to follow some rules. Okay, so we will go through the definitions. So basically our goal is to find out the equivalent states, and we will replace those equivalent states by just one state, and that will represent all those states. Fine. So I will look at the definition of equivalent states. Fine. States P and Q will be equivalent if transition from state P over a string W reaches to the final state, then transition from state Q over the same string W should also reach to any of the final states. Otherwise, if the transition from state P over string W is not reaching to the final state, then the same thing should happen with Q also. That means the transition from state Q over the same string W should also not reach to any of the final state. Fine. So you may not be getting all the points here, but with the example this will be very clear. Okay, here this W is the string. Here if the length of this string is 0, then we will say that P and Q are 0 equivalent. If length of this string is 1, then P and Q are 1 equivalent. If length of this string is 2, then P and Q are 2 equivalent. So on. If length of this string is n, then we will say that in general P and Q are n equivalent states. Fine. So our goal is to find out the equivalent states, and then we will group all those equivalent states into a single state. So let's take an example and discuss all the things on that example. So here we have taken this DFA, and for this DFA we have write down the state transition table. You call this DFA as state transition diagram, and we can write state transition table from this diagram. So now our goal is to find out the minimal DFA from this given DFA. We will apply the procedure that will convert this into a minimal DFA. So the first step is we will check for the unreachable states in this DFA. Check for unreachable state or states. Fine. So unreachable state is a state that cannot be reached from the start state. Here you can see that you cannot reach to state Q5 from start state because there is no path reaching to the Q5. So here state Q5 is our redundant states. It is not required because we cannot reach to this state. So we will directly delete this state. So we will also delete this state from the state transition table. We have this Q5 and this is not needed now. This is redundant. So we can delete this entirely. So now our DFA is containing only 5 states, and now all the states are reachable from the start state. Only one state was unreachable, that we have deleted. Now we will apply the next steps of the procedure. So in our second step, we will check for the equivalency. Now first of all, check for zero equivalent states. So zero equivalent states can be written into two groups of final and non-final states. One group will be of all the states that are non-final states, and one group will be for all the final states. Here only one state is a final state, so we will write Q4 in some other group. So here we have got two groups of states, and all these states in this group are zero equivalent to each other. Fine. Now we will check for one equivalent states. We will take all these 4 states and we will check whether these states are one equivalent or not. So let's start checking one by one. First of all, check Q0 and Q1. Q0 and Q1. On input symbol 0, Q0 is going to Q1, which is in this set. You can call this as S1 and this as S2. Q0 on input symbol 0 is going to Q1, which is in S1, fine. Q1 also on input symbol 0 is going to Q1, which is in set S1, fine. Q0 on input symbol 1 is going to Q2, which is set S1, fine. Q1 on input symbol 1 is going to Q3, which is also in set 1. So if the transition are going to the same set, then we can group those states. So here you can group Q0 and Q1. Q0 and Q1 are one equivalent also. Now we will check Q2. So we can check Q2 with any one of them, but let's choose Q0 for checking. So now we will check Q0 and Q2. Q0 on input symbol 0 is going to Q1, which is in set 1, fine. Q2 also on input symbol 0 is going to Q1, which is in set 1. So this is fine. Now we will check for, we have to check for all the input symbols, okay. For 0 it is going to in same set, but we have to check for other input symbols also. Q0 on input symbol 1 is going to Q2, which is in set 1, fine. Q2 on input symbol 1 is going to Q2, which is also in set 1, fine. So Q2 will also be one equivalent to all these states. Now we will check for Q3. So Q0 on input symbol 0 is going to Q1, which is in set 1, fine. Q3 on input symbol 0 is going to Q1, which is also in set 1, fine. Now we will check for other input symbol. Q0 on input symbol 1 is going to Q2, which is in set 1, fine. Q3 on input symbol 1 is going to Q4, which is in set 2. Here Q0 and Q3 both are going to in same set S1 on input symbol 0, that is fine, but on input symbol 1 they are going to different sets. In this case, Q0 and Q3 cannot be equivalent states, so we will separate these states. So here only Q0, Q1 and Q2 are one equivalent to each other, and we have to write Q3 in separate bracket. And here, since this is only one state, so we need not to check in this set. Okay, Q4. Now we will check for two equivalent states. So now we have three sets. One is your S1, one is your S2, and one is your S3. So now we are checking for Q0 and Q1, and we are checking for two equivalent states. So Q0 on input symbol 0 is going to Q1, set 1, fine. Q1 on input symbol 0 is going to Q1, which is also in set 1, fine. Q0 on input symbol 1 is going to Q2, which is in set 1, fine. Q1 on input symbol 1 is going to Q3, which is in set 2. So here again Q0 and Q1 are not going into same set on input symbol 1. So Q0 and Q1 are not two equivalent to each other. So we will write Q0 and Q1 in different groups. So Q0 and Q1. Now we will check Q2. So we will check Q2 with Q0. Both Q0 and Q2 are going to state Q1 on input symbol 0. State Q1 is in set 1, so this is fine. Q0 on input symbol 1 is going to Q2, and Q2 on input symbol 1 is going to Q2, which is in set 1, fine. Q0 and Q2 can be grouped together. So now we have got 4 sets from S1 to S4. Now we will check for 3 equivalent states. Since there is only one element, so we will not check in this group. We will check in this group. You can see Q0 and Q2 both are showing the same behavior. So these are 3 equivalent also. Both are going into same sets. So if we will try to write 3 equivalent states, then we will get only 4 sets, and there is no change from 2 equivalent to 3 equivalent. So whenever we will get the same number of sets, then we can stop our procedure at that point. We can say at this point that these groups will not change if we will go to any number of equivalency. So we have to take at least 4 states in our DFA. If you will calculate 4 equivalent, 5 equivalent or n equivalent, then there will not be any change after this 2 equivalent. So we can say that, you can say that these are your minimal states for your automata. Now we have to choose the representative states of these sets. Since there is only one state in these 3 groups, then we have to choose that state. But here there are 2 states in this group, so you can choose any one of the state as the representative of this set. Okay, so let's choose Q0. We will replace Q2 by Q0 in the state transition table. So we will replace Q2 by Q0 in the state transition table. So here you will get Q0. Here also you will get Q0, Q0 and Q0. So now our state transition table will look like as, so this is our minimized state transition table, and we can also draw state transition diagram for this table. So if we will draw, we have Q0 as our start state. Q0 on input symbol 0 is going to Q1, and on input symbol 1 it loops itself, fine. Q1 on input symbol 0 loops itself, and Q1 on input symbol 1 is going to a state Q3, fine. Q3 on input symbol 0 is going back to Q1, and on input symbol 1 it is going to Q4. that is your final state also. Q4 on input symbol 0 is going to Q1 and Q4 on input symbol 1 is going to Q0. Fine. So if you will see that, so if you will see our initial DFA was containing 5 states and our minimized DFA is containing only 4 states. So if you will follow this procedure, you can minimize any DFA. Now discuss just one thing, that how we were getting this 0 equivalent, 1 equivalent and 2 equivalent states. Fine. So 0 equivalent states means the states that are together are not going to final state or together going to final state. You can see that if we will not apply any input symbol, then only Q4 is the final state. Okay, so Q4 is going to, you can also say that Q4 is going to final state without any symbol, because this is a final state, and all the other states are not going to the final state because all are not final state simply. Fine. Now check for one equivalent states. So one equivalent states will be those states that can reach to the final states by just applying a input of length 1. Fine. So you can see that Q0, Q1, Q2, Q0, Q1 and Q2 cannot reach to the final state by just applying input of length 1, because if you will apply the input of length 1 at Q0, you will reach only Q1 and Q2 that are not final states. If you will apply the input of length 1 on Q1, you will reach either on Q3 or on Q1 itself. Here also, here both are not final states. And Q2 also, for Q2 also, if you will apply input symbol of length 1, so for 0 it is going to Q1 and for 1 it loops itself. That means you cannot reach from any of these 3 states to final state on input symbol on input of length 1. That means all these states are one equivalent states. Now you can see that Q3 can reach to the final state by just applying input symbol of length, by just applying input of length 1. Okay, if you will apply 1 at state Q3, then you can reach to the final state directly. So here Q3 is separated from all these 3 states. You can see here. Okay, if you will check for 2 equivalent states, so 2 equivalent states means that you can reach to the final state by just applying input of length 2. So now check in the DFA for 2 equivalent. You can see that Q0 and Q2, Q0 and Q2 cannot reach to the final state by applying input of length 2. Check. At Q0, if you will apply input of length 2, either you will reach to Q3 or Q1 or Q2, but you cannot reach to Q4. Fine. The same case is true for Q2 also. You cannot reach to any of the final states since there is only one final state. So you cannot reach to Q4 by applying input of length 2. So Q0 and Q2 are 2 equivalent because both of the states cannot reach to the final state. But we have separated Q1 from this set. Why? Because Q1 can reach to final state by applying input of length 2. Okay, by just applying 1 and 1 you can reach to the final state. So Q1 can be separated from this set. Fine. So you can check for 3 equivalent states also. Okay, so this is very simple. We have discussed this in our definition also. Our definition was that we will say 2 states P and Q as equivalent when both the states either can reach to final state on input symbol W or both cannot reach to final state. Then we will say that those states are equivalent. Okay, so hope you enjoyed this video. Please subscribe to our channel. Thank you for watching.